Hi, everybody. So, I'm the Chief Business Officer at Syntiant. My name is Mallik Moturi. Today, I'm here to talk about and actually to discuss the topic of why we need neural native processors and what are neural native processors. I'll be kind of hone in on that a little bit, and why they're really necessary for enabling these deep learning on the edge. Okay. And I will also kind of at the end talk about how, because of these neural processors or neural decision processors we call them, we are able to enable, we enabled 20 million devices with our chip in the last less than 2 years, and how, along with Edge Impulse, we have been able to enable more than 1,000 customers with many, many thousands of projects, and all in the last year with Edge Impulse. So this is my topic and what I want to talk about. So the focus of Syntiant. So why do we do what we do? And what do we do, right? So why do we do? So what we started off looking at was, if you look at the keyboard, it's an interface that humans used in the 80s, and even today we all use it. But it's still about 150 million units a year are sold with keyboard. If you look at the mouse, in the 90s, it grew the number by, to about half a billion users and units per year. And now we see that with the enablement in the late 2000s, mid 2000s, with Apple, the touch really enabled another 3x increase in the user interface with about 1.5 billion units per year. And what we believe is the next phase or the next interface is going to be this natural interface where you're going to bring all these kind of sensors of motion, smell, temperature, those kind of sensors, and bring them into a natural interface where humans can interact with, along with audio, acoustic events, and speech and voice and vision, right? So these are all sensors, these are all the real world things, and how do you bring those into the digital domain? So that's the natural interface, which will be, I think, much more something in the tens of billions of units. So that's what, why we do what we do. And what do? We bring deep learning to the edge with these purpose-built neural decision processors. So let me talk a little bit, give you a story about how we got into this and what are the requirements. So we spoke with customers when we started the company saying, what do you need? So we spent a lot of time with some hearing aid companies, mobile phone companies. They said, well, first of all, some of them would say, oh, privacy is a big deal. I cannot send anything to the cloud. I want all of this processing to happen right on device. Other one would say, or they would say, it has to be very quick. The interface is it cannot be slow, or high reliability. And these are things you heard, but there's one thing which we heard across the board was it has to be energy efficient while doing all these kind of processing today, which we are sending it to the cloud. So if we are doing speech recognition or doing some audio sensing, that cannot go to the cloud. It has to happen. Processing has to happen on device. So energy efficiency was important. So all the success depends on bringing all this together. So what is driving deep learning on the edge? There's a big market. And as I said, we sold 20 million chips or different domains, but it's only scratching the tip of the iceberg. If you look at the amount of opportunities where you need these rich and robust natural interfaces across from mobile to consumer to enterprise, every use case, I'm receiving all kinds of customer interest for all our product line. We have now we are into the second generation, moving into vision. But I'm getting interest from them across all of this in areas that I even did not imagine in the past. What's enabling this, what is driving this, is also the tools and infrastructure. I said all of this is moving from the cloud to the edge, but at the same time, the infrastructure of the cloud, the amount of GPU and the availability of that infrastructure is enabling it. And the tools like what Edge Impulse has built for AutoML are really enabling it because it really helps to democratize the ability to use AI. So we have this TinyML board that I'll talk about in a bit, which is Edge Impulse enabled, and we get to see thousands of customers using it every day. So MLPerf, and the other area is these consortiums like TinyML Commons, the TinyML Foundation, which have really done a great job at boosting this thing, including the benchmarks that they're creating, that we are also executive sponsors, and we promote all these things, right? So let's now just get a little bit lower into what are the challenges that we see in deep learning on the edge. So this is really the key points here are, to build these kind of, bring it down from the cloud to the edge. Unlike data centers, these edge devices have very limited access to power, and operation is all, very low power battery operated devices, power constraint. And then in the cloud, you have immense amount of memory and computational horsepower, but you have limited, if you went to do the same way you did compute using a CPU on device, then how do you access that amount of compute, right? And then size. All these devices, like for example, I mentioned about hearing aids or phones or mobile devices, these cannot be, these have to be very small. And that means not only that, when we talk to the customer, they would say, these things are important, but also the cost has to be low. So that means the size has to be pretty small. So we need a new type of processor. We cannot build this immense processing power required in the edge, which would move that stuff into this edge device using same amount of processing that you have in the cloud. So we needed a new type of processor. And that's what we ended up building. And here's a simple kind of analogy of why power constraint is such a critical piece. So if you look at an example of the incandescent bulb, right? It's extremely high energy, it's not amount of power required, it's energy inefficient. But, and then you burn a lot of energy and you run it for if you want to run it all the time, like in the cloud. On the same way, the LED, you can leave it on all the time, and there is really, the example is here is, you can be, almost like, almost no power, or you can, it's just very, very little power compared to the, you can even harvest energy from the environment and power LED. But at the same time, deep learning requires an immense amount of processing for instance of time when you're doing inference. We're not doing training, we're just doing inference. And that is like example here is a camera flash bulb going off. So instantly it has to go off, at the same time consume very low power. So if you can reduce the amount of time that you actually you run this energy, then you have a solution. So now I want to give you the key here is I'm kind of giving you the formula of why we were successful in building our devices. So many of you electrical engineers are very familiar with this equation of how power is half CV, energy is half CV squared and multiplied by frequency. And then, and then more in the device physics, there's a static power consumption. So you added, if you look at these 5 variables on this formula, these 5 variables, including reducing the switching frequency, that can be achieved by very clever design, or total capacity, and gives you a quadruple, it gives you a quadratic saving in power. So you can run, if you want to run it at low frequency. You want to reduce the capacitance. If you have a good designer, you can design it such that you have a low capacitance. And then the supply voltage with process, you can work with low voltage nodes and reduce. So all these are good, but there's one secret factor that you need to manage, which is the activity factor. If you look at the activity factor, that's actually our favorite thing that we handle, but where it actually determines how many bits are toggling, how much data is actually moving. So if you can compute at memory, or very close to the memory, you do not need to move the data around from one outside memory or internally or externally. So then you can actually reduce the activity. On top of that, if you can take a neural network and segment it into different parts. I told you there's a neural, natively neural, and move it around so you can actually run the network in different domains while you're doing different workloads. And so turn most of it off so it reduces the activity. So this is the secret for optimizing and keeping the power consumption low, just like in an efficient LED, but just reducing the activity factor and then increasing the power, increasing the efficiency of the chip. So this is a key formula that we use. And this actually, the result of this, I told you there were 3 areas. One was power, the other is memory and compute. It actually kind of solves a lot of those issues. So we solved the issue with bringing the memory and the compute close together. Very high efficiency multiply and accumulate, which is a key for deep learning. And that one we get to up to 80% utilization because of the architecture, our custom architecture for doing this. This is the secret of what neural decision processes have. The other is the natively we process the network, so you do not need another intermediary compiler to go from TensorFlow, for example, to our device. You can go directly on it. And then we have this tightly coupled memory and multiply and accumulate. These are all, so the dividends it gives us is huge. If, for example, compared to an A53 or an A55, for that matter, at a gigahertz, you will have at 1% of the energy and running it at a low frequency. All of these things I was talking to you about earlier actually helps us. So we get an advantage of being able, just to give you a big picture, 6 milliwatts, we can do an image which analyze what is in the image compared to what an A53 would take, about a watt of power. So other thing that we get out of this kind of very close collaboration, close design principles, using these design principles, are the size. Size also, we can build a large network, which is probably one of the largest in this power and this size, and we can do all of those neural network-based sensor interfaces, vision, audio, image, concurrently and with very high efficiency in a small footprint. Like our NDP 115, neural decision, NDP 115 is about 2 by 2 square millimeters, and the NDP 120 is about 3 by 2.5. So it allows us to build these efficient small footprint devices. So what does this actually mean for customers? As I said, we have shipped millions of devices. So that actually the first thing that our customers loved was the size, the power, and the cost. And that allowed us to ship a large number of customers. Then before Syntiant, you were more like tens of milliwatts to do the same function. So for example, speech recognition would be about 10 milliwatts even on a low-end MCU. With our last year, and then we will build devices and boards, and so what NDP 101 enabled last year, we, along with Edge Impulse, launched the Syntiant Core 1 based TinyML board. It was smaller, lower power, and more efficient than anything before that. So last year we launched it, and within the last 6 months, we have seen thousands of users jump on the board and lots of use cases that they have, projects that they launched on the Edge Impulse platform. So that was last year. So this year, we are launching, not yet publicly announced, but there is another device, another even smaller, and with the next gen Syntiant Core 2 that we are launching very shortly, which will have, additionally, we will be processing image as well as speech and sensors. So this is what we're doing, and this is pushing the envelope thanks to the collaboration with Edge Impulse, with us building these next and better and better neural decision processors. So in summary, deep learning on the edge has many advantages. We have to find the killer app and, of course, grow the volume of number of chips that we can sell as we are a semiconductor supplier. But we also are looking at how it helps and empowers a large customer base to users to use it. But it comes with its own challenges. So because we build the neural processor, at Syntiant, we have dedicated to kind of keep pushing that envelope with the Syntiant Core 1, Core 2, and the Syntiant Core 3 coming in the next year. So that's my end of my talk. Thank you so much.